And welcome back to our final talk of the day, last but not least. And please welcome our lovely speaker, Nemanja Milicević, who will tell us how to build something beautiful with Kafka Streams and TensorFlow. So please, the stage is yours.
Hello, everyone. Today, I'm going to focus on the real-time personalization with Kafka Streams and TensorFlow. And before that, I'm going to talk something about me. I'm a software engineer at SmartCat, and I've been there for almost 5 years. Currently, I'm focused on building real-time analytics and stream processing. Earlier in my career, I started as a data scientist, but now I transitioned more into engineering, and I refer to myself as a recovering data scientist. That gives me a good position to see this system that I'm going to talk about from both perspectives. But today, we're going to discuss it from the software engineering perspective. Nevertheless, we need to cover some key concepts about recommendation systems before, just to set up the context for the rest of the presentation. So let's start with why. Why should we care about real-time personalization at all? When we compare the real-time personalization of real-time systems at all to the batch system, we see that there is additional computational complexity. They tend to cost more, and we don't get the benefits of economies of scales. And also, there is incurred operational complexity because we must run the real-time systems all the time, and we have a tight coupling between the computing and the serving, meaning that if our computing part fails, we won't have any results for serving compared to the batch part, where we can serve the previously calculated but stale results. Also, we have low latency, high throughput requirements often, and we must have uptime of 24/7. So just be prepared for pager duty and on calls. And at the end, if you don't have a really strong case for real-time recommendation, just stick to the batch one. Your life will be much easier. There are some times when you must have a real-time part, and these are situations where our customer journey is mission-centered to our business, and when our decisions, our recommendations are time-sensitive. For example, shopping in the e-commerce site is a mission-centric activity, and we also must include the recent user activity there, so we have to be time-sensitive. Also, we need to think about the context when making recommendations. For example, if we are currently purchasing something, we must consider our shopping cart or purchase history, or for movies, recently watched movies, or dislike content on social media. So we need to have that context around us so we can have really valid recommendations. Next, real-time recommendations are really good when the majority of our users are relatively new to the platform, because when the users apply or register to our platform, they don't have any activity. So we don't have any material to have a personalized recommendation for them. So we must quickly adapt to their behavior. And finally, if our competitors have the real-time part, we just have to keep up with them, because often it's a killer feature. Maybe the most notorious recommendation engine you can find is Monolith in TikTok or Instagram. Just insane how fast it works and adapts. And when we talk about recommendation system, we have to analyze them in 4 aspects. One is we have collaboration-based recommendation systems. These are most widely known. We are analyzing user behavior, and users collaborate in order to give recommendations to each other, in a sense. Also, we have content-based recommendations, which are really great because we are using the item metadata. This is especially important when there is a lot user activity or user features, so we must rely on the content. And content-based are really great when we have a lot of items to recommend or they're updating a lot. Also, we can classify recommender system into item to item. So we are answering the questions, hey, given this item, recommended the similar ones. For example, if we are on the movie page on IMDb, we have that section more like this, movies. And finally, we have the user-to-item recommendations. Well, these are probably the most likely occurred in our everyday usage of any platforms. So we answered the question for the given user recommended relevant stuff. So these are the recommended for you sections on the YouTube, on the Amazon, or social media. And in this session, we are focusing on the content-based user-to-item recommendation systems. When we talk about system design of recommendation system, we must first have two separate environments. Usually these think for machine learning systems in general, also for recommendation systems. We have the offline environment where we train our models, build the artifacts, and we have the online environment when we run the inference and run predictions. So we have the two main components in recommendation systems, like this, the basic architecture of any recommender. We have retrieval phase and we have ranking phase. Retrieval phase is crucial for reducing the search space. Imagine that we have millions or billions of items relevant for recommendations. We don't want to score them. We don't want to score each of them. So we want to do some high recall pass to select the candidates. And we are reducing for millions to hundreds or thousands of relevant candidates. And after we got the candidates, we are ranking them usually with some trained classification or learning to rank algorithm. In the offline part, we first have to build an embedding model because we want to efficiently search the relevant recommendation items and build the approximate nearest neighbor index. Then we want to use the item and user data to build the features and to train a ranking model. So we prepare the artifacts that's going to be used in the online part, where when on each new item, we embed the item, get the relevant candidates, enrich it with the features, and finally rank them and serve. So there is that communication between the offline and online part. In terms of artifacts. So artifacts that are required for the online part will be the embedding model, will be the ANN index, will be feature store or access to features, and finally the ranking model. And this session will focus on the online part, on the real-time inference. So we have a question to answer. Given the required artifacts provided by the offline environments, we must answer how to serve the machine learning models efficiently, how to access the features efficiently, and finally, how to maintain high availability while we are still running a low latency, high throughput inference pipeline. So these are the key challenges with any real-time machine learning system. Now, if you zoom out, you can see that there is actually a little talk about machine learning here, and from my perspective, that's great because we can focus on everything interesting around there. There is a great paper from Google called Hidden Technical Debt in Machine Learning Systems that covers a lot of aspects of like technical debt that is not that easily seen from the outside. But the point is that we need to put a lot of effort around machine learning to make it work actually. Now we're going to briefly describe the use case that's going to be the center to this session. And we are building a sports betting recommendation system where we have the sport betting events on the input, and we want to provide recommended for you section for users. We have a pseudocode that can describe the inference pipeline. So this is some like Scala-like code. We had sport event feed Kafka topic on the input. We want to run and apply business rules, just filter things out. We also want to unpack event because usually the sport event feed is complex and nested. We want to flatten them out to have the stream of items if you want. Then we want to embed them, retrieve the top candidates, so just to reduce the search space. And here we have the user item pairs, and we want to get to user selections or user recommendation pairs. So we need to group by pairs by user ID, remove all duplicate items because we don't want to recommend the same selection or same sport event multiple times. Enrich with features, run the ranking, sort, and write it to the output Kafka topic. we can identify 3 phases here. So we have the filtering phase, we have traditional retrieval, and the ranking phase. These 3 phases directly correspond to the 3 Kafka Streams applications that are used in the online inference part. So we have the stateless filtering application that just applies the business rules and writes the messages that are ready for the retrieval part. In the retrieval part, we are using Google's scan implementation of approximate nearest neighbor search, which is really, really efficient. And after retrieval phase, we want to rank the candidates. So we need to access to the features, we need to access to the ranking model, and finally, we are dealing with a stateful application here because we have that aggregation from the previous slide. This will be important later when we talk about scaling and high availability because scaling like stateful applications is much harder. If we analyze the input event or input traffic, we can see that there is some seasonality. What's worth mentioning here that at a input phase, we are not dealing with that many messages, so this scale is just like trivial to scale. Occasionally, we have spikes on weekends or the popular sport events, like a World Cup or you have a Champions League or something like that. But in general, we can handle that easily. The problem occurs when we run this through the retrieval phase, where we get an increase of 2 orders of magnitudes in messages. Why? Because we select the candidates, users that are relevant to the given item. So for the popular events, you have the single message in the input, output can be tens of thousands of messages. So that imposes some scaling challenges. And suddenly we are dealing with thousands or tens of thousands of messages per second. From the previous slide, I already foreshadowed that the main scaling issue is the scaling the ranking system. Because we have a lot of messages on the input, the message rate is variable, so we need to really have a pipeline that has a low latency model inference, low latency feature access, and we also must be able to auto-scale rapidly, so to add or remove more instances depending on the input traffic. And the last part is especially challenging if you have like a large state or large feature store. The first step in overcoming selected mentioned issues is the model serving strategy, because we have that hard requirement that our model inference must be a really low latency. Hopefully, we are dealing with a special TensorFlow binary format called serving model, save model. And save model is helpful because it separates the training from the serving, so it doesn't matter whether we train on the CPUs, TPUs, or GPUs. We can serve the given model with the same protobuf format on TensorFlow serving servers using TensorFlow Lite, TensorFlow.js for the browser, or embedding the model directly into our language runtime through the TensorFlow bindings. We are focused on the serving and binding part because that's what we discuss what's relevant to us in the given context. When speaking about TensorFlow serving, we must mention that that's the separate server that exposes serving endpoints. Currently, TensorFlow serving exposes gRPC and REST interfaces. So from our Kafka Streams application perspective, we are querying the serving server for each message. Clearly, the main advantage of this approach is that it's really intuitive and simple to integrate. We have like clean interfaces defined. We also have some power-ups regarding model lifecycle management. So we have features like A/B testing, canarying release, model versioning, monitoring, etc. And we can also serve huge models here because we have the central place where our model live. Major drawbacks are definitely the higher latency because of RPC. Also, SLAs of our streaming applications and serving server are coupled, so we must think about both when defining the SLAs for our Kafka Streams part. And in case of failure, we are losing Kafka processing guarantees because we are outside of Kafka realm here. So we are just leaving the Kafka and we lose the guarantees. Compared to the serving in battle strategy, we have our model as a part of the Kafka Streams application, so it's directly in the same memory space. Definitely the major advantage is we have ultra low latency inference speed because everything's in the memory, there's no network hop, no serialization, the serialization part. And also SLAs are just in single responsibility of the streaming application, and we have all the Kafka processing guarantees. Of course, the drawbacks are analogous to the benefits of the serving model, where we can only serve relatively small models because we load them into memory, and memory gets quite expensive if you have a lot of instances with a couple hundred of megabytes of models. And also, each instance must have the model in its memory. So just suitable for relatively low models. Also, there are no model management features that we previously discussed, so you need to try that like in other ways if you really need that. And finally, some less popular runtimes and languages may have unstable or poor TensorFlow support. Luckily, we are using Python for training and Scala for inference, so we have really good Python and Java TensorFlow libraries. But even though we still had to dig through the TensorFlow Java bindings code to get something to work. It's not that straightforward and intuitive like in the serving case. But we picked this model because it provides us really low latency, and that's what really mattered for us to handling the large variable number of messages. But this is not the whole picture. If we solve the model inference part, if you have the really low latency inference part, we still need features before model inference. So we must also provide a low latency access to our features. Feature stores are somewhat uncharted territory. If you ask the two persons what a feature store is, you'll probably get two different answers. I like to think about feature stores in hierarchy of needs, where majority of the companies and use cases just need an access and a serving, meaning that you can see the feature store as a key value store in the most basic sense, while the more advanced cases treat feature stores with a lot of additional features like the backfilling, alerting, feature selection, etc. So we have a need for access and the serving, like the most companies. And depending on the company side, you want to increase complexity of your feature store. So one obvious solution for us was to rely on existing Kafka streams and Kafka abstractions for serving low latency feature access. We opted first for global K-table as a feature store. Global K-table is just an logical abstraction of the Kafka's changelog stream. So abstraction over the Kafka topics, which contains our features. Also, global K-tables are great because they broadcast information to all running streams instances, meaning that when the new feature is calculated, it's almost immediately available to all the instances. And each instance keep a local state store based on the RocksDB, which is extremely performant. So we have additional level of caching, if you wish. In the case of the failure, we need to rebuild the local state store from the durable Kafka topics, so we get that cover as well. But we also have additional resource consumption on the memory and the disk because we are copying the complete feature set local to the application. And also we impose a higher load on the network and broker because we're broadcasting a lot of messages. So quick recap, global K-table was great for us because it has multiple levels of caching where we have ultra low latency for features. We're paying that, of course, with a stateful stream. If we zoom out and see the feature generation process as a whole, we can see that on the beginning, we have jobs that calculate the features, writing them to Kafka topic. Then the features from the Kafka topic are automatically replicated to the local RocksDB stores, almost immediately available for accessing. And also, we are storing the features to the Delta Lake for the offline part, for the retraining, for the building the artifacts. Another way for approaching this problem is to have a separate storage for features. A real popular solution is Apache Cassandra, where we write features to Cassandra, and now applications are accessing features through the network. We have the RPC, but we don't have a state on the application side, so there is a trade-off there. But the point is, you need to start like really the simple for the feature store and gradually increase depending on your needs, because usually you have a lot of open source solutions that are overly complex for the majority of organization. Which led us to the next point or challenge in scaling, and that's maintaining high availability, especially for the stateful part of the whole inference. So we need to just do a quick recap to see how the Kafka Streams applications are scaled. So if you have state changelog topic on the Kafka broker side, and we have a streaming instance attached, inside a streaming instance application, we have multiple streaming threads. Streaming threads are a way of parallelizing the workloads in the Kafka streams. And each streaming thread has multiple tasks. Each task is responsible for the small, isolated part of the state. That's a key for the later part. So each task only sees the small part of the state. So we can scale by adding, obviously, more threads, scaling vertically. Important note here is that the state stays on the same host, so there is no copying whatsoever. But if we add the new instances, we must copy the state from the broker to the new instance. So we must rebuild the local state stored there. So during the rebalances, which are inevitable, we have that state restoration part, which might be the pain point. And to denote that two instances are the part of the same cluster, we just need to set a same application ID in Kafka Streams. So basically, application ID corresponds to the consumer group. So what we know so far about this issue is that we know that multiple instances of the same application must have same application ID. We also know that streaming thread, or more precisely, tasks are responsible for the small part of the state store. But if we are dealing with a global state store, like in global K tables, complete states is copied or available from the local instance. So in case of rebalancing, which are inevitable, we must copy a lot of more data. Rebalancing is problematic because event processing stops until rebalance is complete. And that's what can cause our system to be unavailable. So if our rebalance is really slow, caused by the large state, we can have extended periods of the time where we have unavailability. And that's probably the major drawback of the Kafka Streams as a library, because other stream processing can just have some workarounds around that. Of course, to reduce the rebalance time, we have a couple of options. The first strategy is to just employ some configurations on the broker side or on the Kafka Streams side. The most obvious one is to configure the standby replicas, where some other part of the state is shadowily cloned and it's not active. And in the case of rebalancing or in the case of task failover, that state is almost immediately available without copying in the case of the rebalance. We can further improve that by using rec assignment tags. So we want to place our standby replicas to different recs in the case of rec failure. What we were paying here is that we have additional storage, network, and memory consumption because we are replicating more state than needed for fault tolerance. Next configuration is to reduce the segment size of our changelog state store topics. Why? Because Kafka compaction can only happen on inactive or closed segments. So if our segment is huge, we can have a lot of unnecessary uncompacted messages for the same key, and we are only interested in the last one. So if you reduce the segment size, we can more aggressively compact the state store topic, effectively making it much smaller. But imposed cost here is that more aggressive compaction means more work on the broker side. But overall, if you reduce the size of the backing changelog state store topic size, our rebalance can be much quicker because we are copying way less data. And finally, we can configure the delay of initial rebalance, where we say, hey, let's tolerate rebalance time for some period where you're giving a chance to your application to do partition assignment, rebalance, and complete everything without additional costs. This solves a case when we have a cascading rebalances. For example, if one member of consumer group joins and do the partition assignment, then after some short delay, another one comes, we will trigger rebalance. Then another comes, we will trigger rebalance. So we try to solve that situation here. But we must be aware here, because this is a broker-level configuration, meaning that all other Kafka applications are affected by it. And also, in the case of total node failures or total crash, we may increase recovery delay. So be cautious with that. We can also ask ourselves, what can we do besides changing configuration at the infrastructure level? Like, there are a couple of options. The first one is to provide a state checkpointing feature, meaning that we take a snapshot of our application state, compress it, serialize it, save it to some distributed file system and object storage. So state restorations are much quicker because we are dealing with less data. Unfortunately, Kafka Streams does not provide such feature out of the box, like checkpoints and save points in Apache Flink, but we can implement them ourselves. They're really nice interfaces exposed, so if you want such functionality, you can write them yourself. Also, if you have a strict SLAs regarding high availability, we might consider hot standby clusters, meaning running the complete separate Kafka Streams cluster, doing the same processing, but not producing the final results of the output topic. Of course, we are paying with more resources, more applicational complexity, so this can be considered only when we have like a really strict SLAs. And also, we can move our state to the external storage. We discussed this in the previous slides in the feature stores, where similar to the features, we can have our application state saved in the external storage like Apache Cassandra. And this falls under writing a custom state store category again. So we must do that ourselves. There are some open source versions here. I think the Redis, Elasticsearch, and Apache Cassandra are available. But yeah, you need to double check that. And in the end, when dealing with stream processing, we are usually choosing between the correctness, latency, and cost. Unfortunately, we can only choose two. This relationship is really greatly explained in Google's paper, data flow model, so you can find more details there. But at the end of the day, after we analyzed our business requirements, our constraints, we might choose the two and just sacrifice the third one. As a final point, I want to present something that's not the technical issue, but still it's important for overall success of the project. Because we are dealing with inherently complex system with uncertainty, we are dealing with stochastic systems, and the two very different mindsets are collaborating on the same problems. So we have a collaboration gap between the data scientists and the software engineers. Fundamentally, they have a completely different worldviews at the beginning without any much effort, meaning that engineers are often focused on building the things given the constraints, while the data scientists or scientists in general want to understand the things, so they may favor other parts. So their goal and priorities or time constraints are often not aligned. Another point of miscommunication is that data scientists often favor model complexity for the sake of the model, while ignoring any technical constraints. So it's really common to have overly complex model that has a huge performance in the offline environment, which is borderline impossible to deploy, or just too expensive. So there is a drift there as well. Also, there is a communication gap because both teams are using a lot of jargon, and data scientists tend to speak in more abstract ways, using a lot of math stuff, advanced machine learning stuff, while engineers try to speak more concretely and also using a lot of jargon. So some knowledge sharing must be there. When it comes to the versioning and reproducibility, this used to be in much worse state than it's today, because traditionally a data scientist sacrificed versioning and reproducibility for iteration speed. But with emergence of MLOps and MLflow-like tools, this problem is basically solved, where you can have the whole experiment version, all the reproducibility patterns covered by existing tools. So there was a huge drift there, but today there is no excuse for not using such tools in the machine learning data-driven systems. And finally, there is a difference in the exposure to risk or the taste to risk between these two teams, where software engineers prefer stable, tested environments. If it works, don't touch it, or move slowly with the live production systems, where data scientists often tend to move fast, experiment, innovate, and break a lot of things. So we need to address that as well. In my experience, running a successful machine learning data-driven projects usually requires a couple of prerequisites. One of them is to have a culture of continuous learning and knowledge sharing, meaning that data scientists and software engineers must collaborate, like hands-on collaboration from the beginning. So they must do code reviews together or model reviews together, share resources for learning. There are a couple of great books here for engineers to get a taste of the machine learning. There's 100-page machine learning book. For the other side, there are books like Pragmatic Programmer, Effective Engineer. So stuff like that can greatly increase the chance of success of the machine learning projects. Also, from experience, we need to include or involve the data scientists in the system design phase, because earlier in career, a lot of times where data scientists were not part of the system design, they just like optimizing for different things. And when you put everything together and want to productionalize that, you just incur into great challenges. So the technical constraints that we discussed that data scientists often ignore must be addressed early in the project. And finally, a culture of rapid experiments and prototyping is essential, because we are dealing with uncertainty. We are dealing with a stochastic system, and a lot of times you cannot know the outcome unless you try and run it. So you must iterate quickly, and failure is a part of the process. Finally, this slide may be offensive to some of you, but at the end of the day, building the successful complex streaming and machine learning process is the technical and the cultural part, and often technology is the easier part. People usually way harder, and addressing any collaboration issues, communication issues from the beginning of the project drastically increases the chance of the deploying such projects into production and providing the value. This is also important because whenever is machine learning involved, you have to do a lot of stakeholder negotiation. For example, if you have a POC or MVP for recommendation and you want to pitch to someone to give you resources to have a real-time part, you first must convince them. You must provide them the evidence that they have return on investment and stuff like that. And in this session, we covered a lot of points, so let me just reiterate to the key ones before we close. So the first point is that we should use real-time personalization only when we are dealing with a time-sensitive, context-dependent, mission-centric recommendations. Otherwise, most likely you'll be better off with batch systems. Also, we must be aware that machine learning part is just a small part of overall solution. So there is a lot of engineering effort involved here. And there is just a whole world not in scope of this session around the MLOps, around the validity of the features, of the predictions, model retraining, monitoring, etc. So that is just a huge engineering effort. And also, we must choose our model serving strategy accordingly, because there are a lot of tools, a lot of ways to build the models, a lot of ways to serve the models. So we must carefully weigh trade-offs between each of them. Also, features and feature stores must be something that's on our mind from the beginning. But we must be aware that we should not fall into the trap of over-engineering feature stores. When you look at industry and open source version of feature stores, these are solutions often run by a huge big tech companies. And there was a trend in industry where a lot of small companies were using like the huge feature stores. So you don't want to overinvest that early in your project, especially that it's a case that most likely you won't need it at all. Like you need a huge organization, multiple machine learning teams, multiple models, features to actually have a value in a complex feature store. And achieving and maintaining the high availability of the stateful streaming application is complex, but a lot of things can be done on the infrastructure level at the beginning, especially in the Kafka and Kafka Streams part. And you can also always solve the problem by throwing more resources on it. But the stateful streams are much more challenging to scale. And at the end, fostering a culture of the innovation, of rapid prototyping, of collaboration between the data scientists, data engineers, or software engineers is determinantal for success of the overall project. That's something that's like a hard lesson. You can find a QR code here. Please scan it and vote, provide feedback. I appreciate it a lot. If you want to reach out, you can find me on the Twitter, LinkedIn, or GitHub. And at the end, thank you for your attention.
Thank you. Thank you very much, Nemanja. So we have a question over here near the pillar. Okay, I see your hand and I see your hand. Please.
Hello.
Hello.
Thank you, Nemanja, for your beautiful presentation. It's very nice. And I have a question according to latency. Did you compare the latency with such systems like Kafka Streams and Apache Flink?
Unfortunately not, because we had some initiative to compare with Apache Flink, but the thing is, with Apache Flink, you need to run a separate cluster, while with Kafka Streams, you don't have that clustering overhead. So we didn't do that yet, but that's something that might be interesting in the future. But Kafka Streams are not considered.
Because the Flink and Kafka Streams has a async, and it allows to to make async processing and decrease the latency.
Yeah, Kafka Streams and Alpaca solutions, something like that?
Yeah.
Okay.
And second question is about the delivery guarantee. Which configuration of delivery guarantee do you use in Kafka Streams? At least once or exactly once?
Thanks God, at least one for this one, because there is no cost or penalties if you lose a message here. But if you want to have exactly once, then it's just another complete different problem. So for this problem, at least once.
Okay, thank you so much.
Thank you. Over here.
Thank you for your talk. Regarding model serving strategies, did you consider using some another model servers, for example, NVIDIA Triton instead of TensorFlow? It has all the probes and maybe less cons.
So something similar to TensorFlow serving?
Yeah, right.
Yeah, when we first we tried TensorFlow serving, and when we got to the part where we have that overhead due to RPC, then we just went to full bias for embedded part, but we haven't tried anything like non-TensorFlow.
So you're serving on CPU only, right?
CPU, yeah, that's
CPU.
right.
So the second question was about TensorRT, and that's not applicable for CPU.
Yeah,
Thank you.
Thank you. Another question over here near the pillar.
Hello. Hey, my name is Milan, and sorry I missed the beginning of your talk, but I'm really interested in the first point. What are the real-time recommendations, time sensitive, if you worked on any, and if you can tell more?
Sorry, can you repeat the last part?
I can repeat. The very first point, real-time recommendations, time sensitive. Have you worked on any, and what it was? Sorry, I missed the
Okay, no
beginning
problem.
of your
Yeah.
talk. I'm
So.
very much interested in that.
Yeah, the use case I presented here is the online sport betting recommender. So you have the live events where things are changing rapidly. So if you miss the opportunity to recommend the live event, then you pretty much like miss that recommendation. And that's the case that we are presenting here.
Thank you. Another question here.
Thank you for interesting presentation. If I understood correctly, you split the data between different Kafka instances. How do you do that?
How do you
How do you split the data between Kafka instances? Maybe
split the data?
Yes.
Okay, so Kafka Streams is just a library, and it's relying on all the features of the Kafka. So the key thing there is to set the right number of partitions so you can parallelize the workload later, if that was the answer, if I get it right. So how do we split the data between the instances, right? Or was it something else?
You showed the slide where you said that on different Kafka instances, there is only a part of features. How do you split them?
So we must use the same, we're using Kafka guarantees, and we are using the user ID as a key, so that each pair of item users ends on the same machine. So we have the subset of the state always available on the same machines.
Thank you. Any more questions? I know that we are looking forward to the after party, but please stay with us a few more minutes. Yes, question to the right.
I didn't get the part about embedding TensorFlow into Kafka Streams application. Why you decided to do it? You said that like when you did this call through RPC, like gRPC or REST, you had some performance issues, or what was the reason?
Like we have an orders of magnitudes increased the number of inference per second, because we are running inference in the same place where the data is, and everything's in memory. But if we run the serving TensorFlow serving server, we have to serialize, send back, and return the results. That's why we opted in for embedded solution.
Okay, thank you.
Thank you. Another hand. Yes, please.
Hi, you emphasized a lot that one of the major problems was the people from different backgrounds. What is the scale of the team when you think that it comes into action, or do you have like a particular example, or is just the data scientists versus engineers?
I have experience with all scenarios. So maybe the main root cause is where you have the two teams isolated from the beginning. Team size usually affects that, because larger teams has a larger chance to have the separate teams. And concretely for this project, at the beginning we had a separate ML team and like engineering team, and we had a lot of communication problems because we just didn't speak the same language. And after we merged the teams, basically it was the Conway slow in practice, where we merged the teams, a lot of our code changed, a lot of our architecture design changed, and both teams learned a lot from each other. So we just hugely increased our output there. So like the Conway slow was really where the software architecture directly is affected by our communication patterns.
And follow up, would you actually recommend the joining the team, or would you like essentially split it into clusters or something? I'm speaking about a project that has about 70 people working on.
70 or 17?
17.
Oh, 17. For me, that's a huge team. I'll definitely split it because of just communication overhead. But maybe the good thing there is to try to first look from the software perspective, from the architecture, and then try to define teams. But 70 is usually way too high for effective team.
Okay, thanks.
Thank you. This might be the last chance to get a pair of socks. So please, wave your hand. 1, 2, 3. All right then. So thank you, Nemanja. It's up to you to decide who asked the best question.
Well, I have a recency bias, so the last question was most interesting, but let's go with that.
Okay, so the
Last
last
question.
one gets a pair of socks. A round of applause, please.
Thank you.